Hello and welcome to this lecture on the Poynting's theorem. Now in nature we have a lot of different conservation laws, and these conservation laws, they lead to what I call as equations of continuity. And this Poynting's theorem, it also happens to be an equation of continuity. And this equation of continuity, it arises from the conservation of the energy. So you could say that the Poynting's theorem is another statement of the law of conservation of energy. So now let us consider a single charge particle Q, which is moving in external electromagnetic fields E and B. And let's say this charged particle, because it is in these external electromagnetic fields, it now experiences a net force, and this force, it moves it in along some infinitesimal displacement vector dl. So now we know that the magnetic forces, they don't do work, because the magnetic forces are always, the force due to the magnetic fields, they are always perpendicular to the displacement. So magnetic forces will not do any work. So the infinitesimal work due to the infinitesimal displacement is only due to the electric field. So this work done dW will be equal to the electric field dot the displacement, and the electric field is simply Q times E. So this is going to be equal to QE dot dl. So this is basically this gives us the rate at which external fields, they can do work. So what we need to do is this dW, let's say this is the amount of work dW which is done in some infinitesimal amount of time dt. Then this dW by dt, that is going to give us the power delivered by the fields, or the external the work done by the external fields, the rate of work done by the external fields. So that is dW by dt, that is also the power delivered by the fields, and this will be equal to QE dl by dt. Now immediately we recognize that this dl by dt, this quantity dl by dt, it is nothing but the velocity of the charged particle. So this is the velocity v of the charged particle. So as a result, the power delivered can simply be written as QE dot v. So let's call this as equation number 1. So this is basically the rate of doing work, by the electromagnetic fields. But we have to keep in mind that this equation number 1, it is valid for a single charge, because we have written this for a single charge. We don't have a relation yet for, let's say I have a distribution of charge, but we can use this relation to arrive at the same for a distribution of charge. All I need to do is divide the distribution into infinitesimal elements, and then apply this on each element, and then just integrate. So let's go ahead and do that. So we will consider now continuous distribution. So let's say I have a continuous distribution of charge and current. So there could be some charge density rho, there could be some current density J, and this is contained within a finite volume tau. And we are assuming, of course, that this medium in which these charges and currents, they exist, this medium is a linear isotropic medium. So now there could be some fields, some electric and magnetic fields which exist inside this. So because of this, now we can go ahead and we can use this and find out what is the power delivered by these fields on this charge and current distribution. But before doing that, we will have to make a small substitution, because here this is for a single charge. So we have Q and it is moving with some velocity v, but here we have not a single charge, we have current and we have a charge density. So in that case, before we get started, we'll have to make a substitution, and this is that familiar substitution that you all had come across in one of the earlier lectures. So charge times the velocity, if I have a single point, if I have a point charge, charge times velocity is equivalent to the current density times the volume. So we can make this substitution, and the moment we make this substitution over here, so this is going to give us, so P, so we have QE dot V. Then this P is going to be equal to, of course I should not be writing like this, because we are talking about an infinitesimal power. So dP is going to be equal to Q and V, this Q and V together, that is going to give us J, we are replacing with J d tau. Then this J, we have to take the dot product with E into d tau. So that is going to give us the infinitesimal power which is delivered. So the infinitesimal power which is delivered to the fields by the fields on an arbitrary volume element, that is J dot E into d tau. So this allows us next to just integrate this, because this can be integrated now. So we can find out the total rate of work done by the fields on the volume tau. This is going to be simply the integral of this over tau. Let's call this equation number 2. So now to proceed, we will make use of the Ampere-Maxwell's law. The Ampere-Maxwell's law, what does it say? It says that the curl of H is equal, curl of H minus the partial time derivative of d is equal to J. So that's the Ampere-Maxwell's law. So we will use this Ampere's-Maxwell's law because the right hand side is J, and this J on the right hand side, there is a J over here. So we will take whatever is on the left hand side and we will replace this J with that. So inserting this equation number 3 into the please read this as, on the right hand side of equation number 2, on the integrand, in the integrand on the right hand side of equation number 2. So this gives us J dot E, integration J dot E is equal to integration of curl of H minus partial time derivative of d dot E into d tau. So here we have we have J dot E is equal to, we are writing it like this. So E dot curl of H minus E dot partial derivative of t. What we have done is we have just opened up this bracket and used the distributive property of the dot product, and so we are taking the dot of the first term with E and the dot of this time derivative with respect to E. So now we will be making use of an identity, because we need to simplify this one in a form which we can easily handle. So to simplify this, we make use of a particular identity. This is the identity, that is it's basically a product rule for divergence. So if I have a cross product of two vector fields, then the divergence of this cross product is given by this. So let's say this is the first vector. Let's give this a number. So this is vector number 1, because in cross product the order matters. This is vector number 2. So what you do is take the second vector and dot it with the curl of the first vector and reverse the process. Take the first vector and find a dot of this with the curl of the second vector. So this is the identity that we are going to make use of here, and I've just taken this from Griffiths. It's the exact same thing, just I have, instead of A and B, I'm using M and N over here. Just M and N, they're just arbitrary vector fields. So we make use of this. So what we do is we rearrange this, we bring the this term, okay, M dot curl of N, we bring it onto the other side, and this gives us N dot curl of M minus divergence of M cross N. So now what we'll do is we will replace this with our fields. So what we have here is this M. This M, if I replace with E, the vector field, the electric field, and N if I replace with the magnetic field B, then here we'll get a magnetic field, and here we'll get an electric field. Similarly, here we'll get an electric field, and here we'll get a magnetic field. So making this substitution, this gives us E dot curl of, sorry, I'm not using, my mistake here, it's not B, we are using H instead of B. Let me just make this correction here. So we are using H. We are using the H field here. So now this gives us E dot curl of H is equal to H dot curl of E minus the divergence of E cross H. So we can go ahead and we can replace this with these two terms. So now using this equation number 5 in equation number 4, this gives us this expression. So we had two terms here. Now this first term, we'll split it into two more terms, that is these two terms. Okay, so now having got this, so we'll now make use of the Faraday's law. So what does the Faraday's law say? The Faraday's law says that curl of E is equal to minus dou B by dou T. So we are using the partial time derivative with respect to B. So now this is this curl of E over here in equation number 6. So we have a curl of E over here. This curl of E will get replaced with the partial time derivative with respect to B. So substitute using this equation number 7 in equation number 6, we get the left hand side remains the same. On the right hand side we have H dot partial time derivative of B minus divergence of E cross H minus E dot the partial time derivative of D. So this is what we get. Now just a little bit of rearrangement. So I take this curl, I take the minus sign common outside the integral, and we take this first term, that is that which contains the E cross H, we'll take it here, and the other two terms which contain partial time derivatives, we'll just collect them together and we'll keep it aside like this. So this becomes our equation number 8. So now this equation number 8, to recognize these two terms, I will make use of two results from J.D. Jackson. The first one is that of the electrostatic energy density. We can show that the electrostatic energy density, that is dUE by d tau, the energy per unit volume, it is equal to half E dot E. So you might want to refer to Jackson, this particular section, if you want to know how this has been arrived at. In a similar way, we can show that the energy density due to a magnetic field, it is equal to this half B dot H. Okay, so half E dot E dot D is the electromagnetic energy density, half B dot H is the magnetic energy density, the energy density due to the magnetic field. So this is not the it is the electrostatic energy density, this is the magnetic energy density. So the total electromagnetic field density, the total electromagnetic energy density, the total electromagnetic energy density is going to be UE plus UM. So UEM, the electromagnetic energy density, is equal to electric energy density plus magnetic energy density. So half, I take it common, then the sum of E dot D plus B dot H. So this is the total electromagnetic energy density. So we'll take this, and now we will just take this particular equation and we will use it in we will first differentiate it, because if I want to use this over here, because you can see in the equation that we have established, that is this equation, we have B dot H, and if you want to be and there is a B, we have a B dot H here, so and there is a E dot D, so we have E dot D, but of course we are differentiating one of these. B is differentiated with respect to time and D is differentiated with respect to time. So now if I want to be able to use this, incorporate this UEM over here, the way to do that would be I have to find the partial time derivative of UEM, and that's what we are going to do here. We'll find out the partial time derivative. So we want to find out the time rate of change of the electromagnetic energy density. So the time rate of change, you're differentiating UEM with respect to time, that is going to be equal to, first you differentiate the first term, then you differentiate the second term. Now we will have to use the product rule. As per the product rule, first you have to do is you have to differentiate each of these, because this is a product. The dot product is after all a product, so you have to first differentiate each of these. So first we differentiate E, which will keep D as a spectator, then we'll differentiate D, which will keep E as the spectator, and the same thing we do it over here. So this is going to give us two terms and this is going to give us two terms. Now what we do is we know that D is equal to epsilon E, because D is equal to epsilon E and B is equal to mu H. So here we are writing D is equal to epsilon E and B is equal to mu H. Why is that so? Because we have assumed an isotropic, a linear isotropic medium. We have assumed a linear isotropic medium, and this implies that D is equal to epsilon E and B is equal to mu H. Okay, so from here we are able to make this kind of a substitution. Now having done that, what we can do next is because epsilon is after all a constant, so you could just take this and bring this inside the derivative, inside the time derivative. Similarly, you can take this H from outside and you can just club it together with this. So epsilon comes inside the derivative, and here mu comes inside the time derivative. And once we do that, again we use this, we recognize that this is actually d again, and this is b again, and this gives us the time derivative with respect to d, and this gives us the time derivative of d with respect to t. Sorry, this is the time derivative of d, and this is the time derivative of b. So we have e dot time derivative of d plus e dot time derivative of d. So these two, when I combine them together, so we'll get a term 2. And similarly over here, these two are identical, so this will give me another 2, and there is a half outside, so the half is going to get cancelled out. So eventually this is going to give us the time derivative of the electromagnetic energy density is equal to e dot time derivative of d plus h dot the time derivative of b. So the vector E cross B, it is in the direction of the electromagnetic wave propagation, we know that. So we could use this to represent the energy flow, the vector E cross B, we could use this to represent the electromagnetic energy flow. So we define a vector called as a Poynting vector. That Poynting vector is defined as E cross H, because E cross B, this is not B, please read this as H here. Of course, I mean, even E cross B is also going to give us the same direction, the direction of the electromagnetic wave propagation. So we define this quantity E cross H. If I want to use B, then I have to divide by a mu. Then the Poynting vector we have to divide by mu, 1 by mu E cross B. Okay, so S we define it as E cross H, the Poynting vector, we define it in this way. Then we recall the earlier equation, the equation number 8. This was equation number 8, and we recall that in equation number 8 we had two terms inside the bracket, actually three terms. The two of the terms, they contain the time derivatives. Here E cross H, we have defined it to be the Poynting vector, and this one we can see here is exactly this same thing. So we replace this second term, we replace it with the partial time derivative of the electromagnetic energy density. And once we do that using these two equations in equation number 8, so this is going to give us divergence of S plus the time derivative of the electromagnetic energy density. Okay, so now we just one step from here, we just use the Stokes theorem. We'll use the Stokes theorem in the next step. So we just do a bit of rearrangement. So this one we bring it onto the left hand side, and we have this minus sign going over here. This one goes here, and then this also we bring it onto the left hand side, and then as a result we will have the volume integral of the divergence of S plus the volume integral of the partial time derivative of the electromagnetic energy density is equal to minus the volume integral of J dot E. So here we can use, not the Stokes theorem, the divergence theorem. We use the divergence theorem, and we find that this is equal to the surface integral of S taken over this S. This S is the boundary surface of this volume, and we have this. So we have these two expressions. So because in equation number 12, d tau is arbitrary, so this we can actually extract the integrants must be the same, and this allows us to extract the integrants, and we can write the same equation in differential form. We can write it like this: the divergence of S plus the partial time derivative of the electromagnetic energy density is equal to minus J dot E. We're just taking this integrants outside because d tau is arbitrary. So this allows us that we can write this in a differential form. So either equation number 12 or equation number 14, they become the what is called as the mathematically is called as the Poynting theorem, and we could interpret this physically as this: the time rate of change of the electromagnetic energy density within the time rate of change of the electromagnetic energy density within a certain volume, plus the energy flowing out, the energy which is flowing out through the boundary surface of the volume per unit time is equal to the negative of the total power delivered by the fields. So these three things, they will appear together because we have used the conservation of energy. So this is basically a statement of the conservation of energy. So we could compare this with the continuity equation that we had arrived at earlier. So the continuity equation is divergence of J plus dou rho by dou t is equal to 0. So suppose I have some volume, some volume tau, and this volume is bounded by some surface S, and inside this, let's say we have some charge density rho, and let's say some current is flowing out of this. The current will flow out at the expense of this charge. So because of the conservation of charge, we cannot create charges, nor can we destroy charges. So if the current is flowing out, then that means the total charge inside should reduce. So that is the base. From there, from that idea we had arrived at the equation of continuity in one of my earlier lectures. So if we compare this equation of continuity with the Poynting's theorem, so we have here also, we have on the left hand side we have two terms. One is a divergence term, another one is a time derivative term. But here, of course, on the right hand side we have 0, but here in the right hand side we have a j dot e. So what is actually happening here? So we could actually bring about, we could do some kind of a substitution if you compare these two scenarios. So what's happening here is this j, the role of j that we have in this side, that same role is being played now by the Poynting vector. And the role which was played by the charge density, the same role is now played by the electromagnetic energy density. And then, but then there is one more difference. The difference is there is a 0 here and there is minus j dot e. So what is the 0? The 0 means there are no sources. There are no sources of charge. There is no source, nor there is any sink of charge. We are not creating, nor are we destroying any charges. That means this side, that means there could be some source which is leading to these two variations in the energy flow as well as the energy density. So where is this coming from? This is coming from the electric and the magnetic field. So we have, let's say, some electric field in this region, some electric field E, and we have some magnetic field, let's say B or H, some magnetic field. So we are having some electric field and magnetic field, and this electric and magnetic field, it is going to cause some kind of because it's going to make the charges move, so it is going to cause some kind of a volume current density. So basically there is a external driving agent which is causing this motion of the charges inside, and when because of this, what is going to happen is the energy, some of the energy is going to be stored in the fields within, and some of this energy is going to flow out. So that basically is the Poynting's theorem. So this shows the physical meaning that the physical interpretation that we have arrived at over here. So whenever we have fields which are present in a region, and these fields will drive maybe some kind of a current density inside, then the energy that is being delivered, the power which is delivered to these charges, a part of this will be flowing out of the system, and a part of that will be stored within the in the fields within the system. So this is the physical interpretation of the Poynting's theorem. So with this we come to the end of this lecture. Thank you.